Hello friends, welcome to engineering tutorial. So today we are going to resume our discussion on control systems, and we will be discussing some more questions on signal flow graphs. I think I have posted around 3 or 4 questions related to it, so I thought maybe I should discuss some more questions so that we understand this concept in a good way, because it is a very important concept. Okay, so this here is a signal flow graph. Okay, and we have to find its transfer function. Okay, so as we have already discussed in the previous questions, and I would like you to please watch all the videos related to block diagram reduction, transfer function basics, open loop, closed loop transfer function, and all the basic concepts related to signal flow graphs which I have already discussed, and the 3 or 4 questions which I have discussed, and then watch this video. Okay, so that you understand it in a better way. Okay, so like we proceed in a signal flow graph as per the Mason's gain formula to find the transfer function. First we have to determine the number of forward paths. Okay, starting from the input node to the output node without any node repeated more than once. Okay, so as you can see, we have a straightforward path here starting from, okay, let us write it down here, P1, which is R, node 1 this, then 2, then 3, then 4, and then C. This is one forward path, and the gain of the forward path is this, the gains of the individual branches. Okay, so here it is G1, here it is 1, it is G2, here is G3, G4, the product. So the gain is equal to G1, G2, G3, G4. That is the first forward path. Then the second forward path. The second forward path is this R, then 1, then C. From 1 to 4 directly there is a connection, forward connection. Okay, 1 to 4 to C. So in this case the gain will be G1, G5, G4. Okay, G1, G5, G4, this. Okay, and there is no other forward path. Okay, so this is the forward paths. Now we have to find the loops, okay, which start and end at the same node. So here this is one loop, as you can see here, loop 1, which is 2 to 3 to 2 with gain minus G2 H1, that is G2 multiplied with minus H1 becomes minus G2 H1. Then another loop is 3 4 3 3 4 3 with gain minus G3 H2 minus G3 H2. Okay, so 2 forward paths and 2 loops. Then the next important thing to find out is the path factor. Path factor, which is for each path we have to determine. So if you have watched the previous videos, path factor basically is those loops, okay, which the particular path has not touched. So for that what we have to do is that we have to find out whether there are any common nodes between the path and the loop. If there are common nodes, it means that the path is touching the loop. But if there are no common nodes between the loop and the path, then that particular path is not touching the loop. I've already discussed about all these things in the previous videos in detail, so please watch those videos. Okay, so here for path P1 with this nodal path, see here 232, here 23 is present. It means P1 is touching L1 because there is common node between P1 and L1. Now 343 loop L2, here there is 3 and 4 present, 3 and 4 node. So it means this path is touching these loops. So P1 is touching both L1 and L2. So the path factor for P1, it is given by the formula 1 minus sum of the loop gains of the loops which the path has not touched. But here it is touching every loop, so it is 0. 1 minus 0, which is equal to 1, because it is touching all the loops, so it is 0. It is 1 minus 0, 1. Next, for loop for path 2, R14C, here P2 and L1, see there is no common node between P2 and L1. 232 is not present at all in path P2. It means it is not touching loop L1, but it is touching loop L2 because 4 is present. 4 is present here in path P2 and also in loop L2. So P2 is not touching L1. So the path factor for path 2 is 1 minus L1, loop gain L1, which is equal to 1 minus G2 H1, which is equal to 1 plus G2 H1. So we have found P1, P2, L1, L2, this delta 1, delta 2 path factor for P1, path factor for P2. Now we have to find whether there are any non-touching loops, that is two loops which have no common nodes in between them, or they are not touching at all. But see here, these two loops, they have node 3 in common, so they are touching each other. There is a common node, so there is no thing of non-touching loops here. So we have found out all the related things for the Mason's gain formula. Now we will find the gain. So we have determined all the things which are required to be put in the Mason's gain formula. Now we have already discussed about Mason's gain formula in the previous videos related to signal flow graphs and transfer function calculation determination. So as per the Mason's gain formula, the transfer function, it is given by, okay, 1 when k by this. So here we all know this is the product of the path gain and the path factor depending on how many number of paths there are, and then we have is the signal flow graph determinant, which is 1 minus sum of the individual loop gains plus sum of the gain products of 2 non-touching loops minus sum of gain products of 3 non-touching loops, and so on. Okay, so here we have only 2 paths, so here this expression will be P1 delta 1, P2 delta 2, then 1 minus L1 plus L2. There are no two non-touching loops or three non-touching loops, so everything is not required. So this will be equal to P1, G1, G2, G3, G4, delta 1 is 1, it is 1, plus P2, G1, G5, G4, then delta 2 path factor for path 2 it is 1 plus G2 H1, then 1 minus sum of the individual loop gains, that is 1 minus G2H1 minus G3H2. So when we remove the bracket, it will become plus 1 plus G2H1 plus G3H2. Okay, so this is the transfer function for this signal flow graph here. Okay.